Can we open to page 39 in the packet? And while we're opening to page 39, we will pull up our calendar and have a look. So we are here. The topic for today is the second derivative. Just a reminder of where we've been. The last class, we had two main goals. We wanted to look at all kinds of different notation. We have different notation because we have two different people who invented the calculus sort of at the same time but independently of each other. We introduced Leibniz's notation. We actually don't use Newton's notation for the derivative, which was that dot on top of the function. We end up using the prime, which was due to another mathematician, Lagrange. So we talked a little bit of history last time, and we also talked about the notation, and then finally interpreting derivatives in unfamiliar contexts. What does it mean to talk about a derivative in a space where you've never really thought about rates of change? So those were the two main things for last class. And today we talk about the second derivative. And just a reminder, what's coming up next class? We have our second quiz next class. It is on classes 5, 6, 7, and 8. Today's class number 8. So it should be pretty clear to figure out what's going to be quizzed on that quiz. And then the 26th, I guess that's the Wednesday. Is that right? So on Wednesday, project number 2 is due. Some folks have already gotten a jump start on things and started looking at it. I'd encourage you to look at it sooner rather than later. Does everybody have a copy of the quiz? Sorry, the project? Yeah, I generally don't give the quizzes out ahead of time. Okay, and then, so today and then tomorrow is the last day of new material before our first test. So we'll talk about this idea of differentiability on Monday. Wednesday is our review, and then Friday is the test. And the idea of having the quiz on Monday is that I can give it back to you Wednesday so you can have some more feedback before Friday's test. I've thought about this. Any questions on the calendar? Nikki?
A couple of times in our packet, it makes reference to study guide for test.
Yes, let's take a look at the study guide for test number 1. I don't know exactly where it is, but it's a little further on in the packet. If somebody has a page for me, let me know. There it is. 50. Yeah, it starts on 50, and then, yeah. So also not too early to start studying for the test, and there are references to this study guide. It starts on page 50. It begins with a list of things that I'd like you to be able to do. So there's a long checklist. You can go through one at a time. Then there's a list of resources for the test. Here are some problems that have never been assigned for homework, but might be good for extra practice. Also going over old homework assignments and quizzes, and the sample test problems, which we'll look at momentarily. And then it talks about how on the test, so on the quiz, you can bring an index card of reference material, and you can do that again for this coming Monday's quiz. I have index cards here if you want one. They're also on my office door. But for the test, it's a bigger thing than the quiz, so I give you a bigger piece of reference material. So an 8.5 by 11, a full piece of paper, front and back, write or type anything you want on that in preparation for the test. Graphing calculator for the whole test. And then here are the sample test problems. And so you can start taking a look at these. And maybe just while we've got this up here, I'll go ahead and pull up the YouTube page because I've added something new in the last few days. So let's see if we can find me. So that's my YouTube username, and that's my channel. And inside of here, if you go to playlists, you'll find, and if you didn't get all that, there's actually a direct link to the sample test problems on the syllabus. So just go to the syllabus if you want. So a few days ago, I added the videos for the sample test number 1 problems. So we'll pause this and just kind of fast forward here for a moment. The problem number 1 has to do with a population of 10,000 people. And if you go to that very first video, it's that problem about 10,000 people. And so you'll see me solving it all the way out, and you'll hear me talking my way through it. And I made a different video for each of the sample test problems, and they're all in that playlist. I've also put up on Moodle the PDF of these sample test problems completed by me. You know, like I filled all the details in on the packet, and so I made a PDF, and that's on Moodle right now. Nikki, is that good? Okay. Any other questions on the calendar? All right, then let's come back here. And what page were we starting on today? 39, maybe it's around here. Okay, so we'll go ahead and start with number 1. Andrew? Okay, so we've already seen the derivative of a function, but we can think of the derivative of a function as its own brand new, perfectly legitimate function. So if I wanted to take the derivative of the derivative, we would call that the second derivative, also the name of today's class. So that's the second derivative. And then here's some notation for the second derivative. All of these 4 things mean second derivative. So f double prime of x, makes sense, put 2 primes, means 2 derivatives. Then we get into this kind of funny looking thing here, this d squared over dx squared. There's actually another one right there. And so this is this is Leibniz's way of writing things. Do you guys remember d over dx was Leibniz's way to say the derivative of? Just like a square root symbol means the square root of. This is the derivative of. So if I wanted to take 2 derivatives, I would say, okay, the derivative of, and then I'll write the derivative of, and then maybe you put the function over here, f of x. But then instead of writing that all out, we'll kind of treat the d's as being numbers, and this as being multiplication. So what is d times d? D squared, that's the d squared that's circled on the top in the purple thing here. Dx, thinking of dx as one symbol, dx times dx is dx squared. Technically, we should put parentheses around there to really show you it's not just the x being squared, it's the whole thing, it's dx. But nobody feels like writing that, so we don't. And then the same kind of thing in the second purple, this thing right here, that d squared, dx squared means take the second derivative of, and then it's y in this case. And then finally, y double prime. Good? Okay, so let's move on to number 3. Joe? I skip down to 3. Okay, so let's try number 4. Nikki?
Second derivative that s of t. Then s prime of t will change in position, right? And s double prime of t change in.
Okay, so change in position is better known as velocity. So that's the first derivative of the position function or the height function. So we've seen examples like that from day 1 in this class. And that means that the second derivative must be the change in the first derivative. And what word did we just say is really the first derivative? Is velocity. Everybody see that? Second derivative must be the change in the previous function, the function 1 layer down, which is the first derivative. And what's the fancy word for change in velocity? Is acceleration. So we've got kind of this ladder. The position is your original function, and the first derivative is velocity, and the second derivative is acceleration. Okay, now let's take a look at this next piece here. It says, so this is an important sentence. We're going to use this a bunch today. If a derivative is positive, that is the slope of your tangent line is a positive number, that is the tangent line is uphill, yes? If the derivative is positive, then what must the original function be doing? It must be going uphill. It must be increasing, okay? If the derivative of any function is positive, the function itself is going uphill. And then, so people often say conversely, but I don't think that's the right word. It's actually inversely if you're a math person. Inversely, if the derivative is negative, what is the function doing? It is decreasing. That is a fundamental fact. We've seen it, we buy it, we're going to use it a bunch today. It's not hard when we say it in these terms, but it's about to become a little bit murkier because we'll be floating around in different derivative land. So suppose that s double prime of t is positive. So s double prime was our second derivative of position. So s double prime of t is positive. S double prime is a derivative, is a first derivative of what function? Yeah, it is velocity. I want to write it is the first derivative of s prime. We buy it? I want to think of s prime as being the starting function. I don't want s to be the starting function. Now I want s prime to be the starting function. And then s double prime is just the derivative of s prime. So we just saw here in this starred purple thing, if a derivative is positive, the function is increasing. So if f double prime is positive, then what must the original function, which is s prime now, what must it be doing? It must be increasing. And then as Ernie points out, s prime is velocity. So if your s double prime is positive, then your s prime, your velocity, must be increasing. Which I think makes sense. If your acceleration is positive, your velocity is going to increase. Yes? Okay. Now, most of the time, most of our experience involves moving forward. Walking, driving, biking, whatever. We're almost always moving forward. So if we're moving forward and we are accelerating, then we're speeding up, right? But we don't have a lot of practice with this part. If you are moving backwards, but then accelerating in the positive direction, what are you actually going to do? You're actually going to slow down. This would be bad for your car, but if you were going backwards, right, and then you hit the gas, but your car is in drive trying to go forward, are you going to speed up or slow down? You're going to slow down before you stop and then eventually start going forward again, right? So we just don't have as much experience in the moving backwards direction. But speeding up and slowing down, we should be really careful with those words. Okay, now suppose that s double prime is negative. That means that the first derivative of s prime is negative. If a derivative is negative, what is the function doing? It is decreasing. So in this case, velocity is decreasing. So suppose for a second that your velocity is decreasing. If you are moving forward and your velocity is decreasing, are you speeding up or slowing down? Slowing down. You really got to think about this carefully. If you're moving forward but your velocity is decreasing, you're slowing down. But if you're moving backward, then your velocity is already some negative number, negative 10 feet per second. And if your velocity decreases to negative 12 feet per second, then what are you doing? You're going faster, you're going backwards, but you are speeding up. So it's really easy to make the following mistake. If acceleration is positive, I am speeding up. It's not true. We don't have enough information. You need to know which way you're headed. If you're going forward, it's true. But if you're going backward, it's false. Yeah. So for us, velocity being positive could mean, so here's 0 and 1 and negative 1. Velocity being positive could mean you're going to the right in the positive x direction. Could mean you're going up away from the Earth. It could mean you're just going forward wherever you are. In some sense, it's an arbitrary definition, but I'm glad you asked it. Yeah, for us, velocity is going to mean one of those things. Go forward, go to the positive x's, go up, but we'll try to be consistent. Okay, and then finally here, if s double prime is 0, okay, let's take a moment. That means the first derivative of s prime is 0. If a derivative is 0, can you show me what the tangent line looks like? It's this horizontal thing, right? So if your derivative is 0, are you increasing? No. Are you decreasing? No. You are paused. You're not changing at all if your derivative is 0. So if s double prime is 0, then s prime is paused. So what is your velocity? Constant. Not changing. Horizontal. Okay, let's go to Garrett for number 5.
Another place where we have seen the second derivative outside of x. Let f of t equal the cost of standard basket goods and services times t. let f prime of t equal the rate at which costs are changing as time passes.
Okay, let's see if we know this word. The rate at which costs are changing as time passes. Right now, costs go up a little bit. Costs are a little bit more than they were a year ago. It's inflation. Inflation is a derivative. Inflation gives you a sense of how costs are changing as time passes. A rate at which costs are changing as time passes. Oftentimes, inflation is given as a percentage. It's 3%. It's 5%. Okay, that's fine. We could also think of it as a, like a gallon of gas costs, right now, roughly a gallon of gas is, the price is increasing at 5 cents per year. Maybe tomorrow it's 4 cents per year, but it's increasing generally. And that's inflation. And so we keep kind of coming back to the standard thing that I've started up here. If a derivative is positive, then the original function is increasing. So if f prime of t, remember f is the cost of a standard basket of goods. They put a gallon of milk in there, they put some bread, they put like a bar of soap, and it's something that's actually calculated. Like this isn't just made up. You can go out and figure out and find out exactly what's in the standard basket of goods. And they just take a look at the prices of all those things today, and they have some number, and they take a look at how that compares to the number a year ago. That's how we come up with this inflation. So if f prime is positive, then what's happening to the costs? If the derivative is positive, they're increasing. Costs are going up. If f prime is negative, then what's happening to the costs? They're going down. Now, this doesn't happen very often in this country. Usually we're in the positive thing, which is called inflation, but what's it called if costs go down? Is it D? I think this is the word. Talk to somebody who knows economics, but I think it's deflation. If f prime is 0, what are costs doing? They're staying the same. Costs are constant. No inflation, no deflation. Things are just costing the same thing tomorrow and the next day and the next day after that. All right. So we're pretty good with the f prime. It's the rate at which costs are changing. Now we get to the tougher concept, the second derivative. So f prime must be the rate at which what? It's one word, is changing. Inflation. It's a derivative. I don't want you to always look at it as a second derivative. It is a first derivative of some function. It is a first derivative of the first derivative. And the first derivative is inflation. So second derivative must tell me how inflation is changing. Inflation doesn't stay at 3% a year all the time. It doesn't stay at 10% a year all the time. It changes. And if I want to think about the rate at which inflation is changing, that's f double prime. So let's assume that we have inflation instead of deflation. So costs are going up. F prime is positive. If f double prime is bigger than 0, then what is inflation doing? It's increasing. It is a derivative of some function. And if a derivative is positive, then the original function was increasing. So maybe inflation right now is 3%, maybe a month from now it's 4%. That would be f double prime being positive. Inflation is increasing. If f double prime is negative, I'm not saying that the costs are going down. Costs are still going up. But how are they going up? Slower. They're not going up by as much. Still going up. But they're going up less and less. So inflation would be decreasing. But it's still positive, I should say. So the costs of this basket of goods would be increasing, but slower and slower. It means that so we have to decide what function we're talking about to answer any question about increasing or decreasing. So if we are talking about inflation, inflation increasing just means it goes from 3% to 4%, and I can't tell you what it's going to do after that. All I know is it's going up. But what we can say is the cost of that standard basket of goods with all these things in it Okay, we have inflation, so the costs are increasing. But if inflation is increasing, then the costs are going up faster and faster. So maybe that basket of goods costs $10 today, 15 tomorrow, 28 the next day, increasing, but by more and more. Okay, still increasing, still positive, still inflation. But if the inflation is decreasing, maybe it's 4% and then it's 3% and it's 2%, the costs of my basket of goods are still rising. $10, $15, $18.
Concave down.
Yeah, we're going to talk about, we'll use that word concave today, and concave down describes this. So we have to decide what it is that we are talking about. The basket of goods is what we were talking about for a second, with the costs are going up, but by not as much, slower and slower.
First one is
Yeah, so
approaching straight up and down.
so the first one looks like this. The costs, as time passes, the costs are going up faster and faster. But the second one, this guy right here, the costs are still going up, but by less and less. Okay, let's go to 6. Chris.
Bid for re-election back in the fall of 1970. Richard Nixon told the country that the rate of increase of inflation
You have a Nixon accent. Okay, so here's the question: was it reasonable to expect that the U.S. populace would have a clear sense of what he was really saying? Did he have a clear sense of what he was really saying? Okay, so we've already said inflation. Is inflation, what derivative is inflation? It's the first derivative. That's what we said. So inflation is f prime. Then we talk about the rate of change of inflation. So what derivative is that? That's f double prime, because we're talking about how the derivative is changing. That's what we just did up here. But then we go even further and we say that the rate at which inflation is changing, okay, inflation is increasing, but the rate at which is increasing is decreasing. So what derivative is this? That is the third derivative. So supposedly the first time a sitting president referenced the third derivative in a speech to the country. Yeah, what does it mean? Is there inflation? According to that sentence, was there inflation? Yes. Was the inflation going up or down? Up. Inflation is getting worse, right? Generally, we don't want inflation to like be really, really high. Although if you take an economics class, inflation is not like this evil thing. It's part of a healthy economic system. You just don't want it to be too high. Trying to find a balance between inflation and unemployment. So inflation is going up. Things are getting more expensive, but not by as much as they were before. Okay. Number 7, we'll just write in a few of the, we'll skip the units. We did a lot of unit stuff last time, so you guys can fill in units later on. Let's jump down here to 8, and we'll go to Bubba. Okay, so f prime and f double prime. So what I'm going to do is just pick a couple of points on each of these graphs and draw tangent lines. So maybe there's one tangent line, and then there's another tangent line. So first, is f prime positive or negative for that graph? That's positive, because these tangent lines are uphill, positive slope. And then if we just think about the slopes themselves, are the slopes increasing or decreasing? They're increasing, right? The second line was steeper than the first line. Maybe the first slope was 1 and the second slope was 2. So second derivative is positive. Can you guys draw 2 tangent lines on each of these? Or if you don't need to, just jump to the signs, looking for the sign of f prime and the sign of f double prime, and check with your neighbors. Look. So do we agree? Double check my work here. The second one, I got both negative. Third one is a negative and a positive. Fourth one is a positive and a negative. Okay, and now we jump to number 9, and we'll talk about what Garrett had referenced before. Toby? Okay, keep going. Okay, so this is a definition here. I will tell you that the graph, the first graph that I'm showing here, this parabola-looking thing, is called concave up. And so if you're just looking for a way to decide whether a graph is concave up or not, if it looks like a cup, it can hold water, concave up, pretty clever, huh? Is that nice? Yeah. Okay, go ahead, Toby. Yeah, I don't know if anybody else is doing this. I don't know if they're original. I didn't find them anywhere. I came up with them, but I don't know. Concave frown. Uh, but but it's possible other people use it too. Yeah. Okay. So let's look at the second piece. Sorry, the third one. The third graph is part concave up and part concave down. It changes. And so generally what we do is we talk about the x values for which the graph is concave up or down. And so I'll say that like for the yellow x's, it's one thing, and for the green x's, it's another thing. So on this first piece here, what is the graph? Concave. It is concave down. That looks like the start of a frown, and it just doesn't continue. But it's the beginning of a frown, so it's concave down. And then the second piece is therefore concave up, because if that graph continued on its trajectory, it would have been looking like a cup. Any questions on that? Okay. So last sentence here, for each of the four building blocks, the four graphs that are just above, I would like you to choose two of these four phrases. Every graph up there is either increasing or decreasing. Every graph up there is either concave up or concave down. So can you guys just write? And we can abbreviate stuff. So for example, this one right here, the first graph, is it increasing or decreasing? It's increasing and concave up. So I'm just going to abbreviate. So try the other three and double check with your neighbors. Okay, how are we doing with this concave up and down business? Okay. All right, so now we're going to try to come up with some conclusion looking at so the idea here is that if you have a graph in front of you, then you can analyze pretty quickly where it's concave up and where it's concave down, where it's increasing and where it's decreasing. But oftentimes, part of the goal of a problem we'll be facing is given the equation, like given the function, the rule, x squared minus 5x plus square root of x. Where's the function increasing and where's the function decreasing? And we're not going to have the benefit of a picture in front of us. So we're going to try to translate from the graphical, looking at the picture, to the analytical, the algebraic side of things. And that's where the signs of the derivative come in. So let's make our conclusions here. If the first derivative is positive, then what's true? The function's increasing. That's the common thread for those two. If the first derivative is negative, then it's decreasing. We knew that before. Okay, now we jump down to the second part. If the second derivative is positive, then the function is concave up. This is the new piece for us. If the second derivative is positive, the function is concave up. We're going to write that on the next page. And then the other side of that, if the second derivative is negative, the function is concave down. So let's fill in the blanks. If f prime of 0, then the graph of f is increasing. First derivative has to do with increasing and decreasing. If f prime is negative, then the graph of f is decreasing. That's old. Here's the new part. If f double prime is positive, the graph is concave up. And then if f double prime is negative, the graph is concave down.
Yeah, well, that's where ABC.
Mm-hmm.
I'm a little confused about, say, for example, if you look at B and D, if you look at our tangent line, you see that the slope is becoming increasingly steep, right?
Yes.
Left to right.
Yes.
But indeed, the slope is becoming less steep as we go from left to right.
That's right.
So I feel like
Yeah, so I think the idea here is that generally we look at slopes and we just call them steeper or shallower, but we don't give a sense of whether they're positive or negative. And the second derivative is really, really concerned with whether the thing is positive or negative. So let's just make up a slope for this one and for this one. So this guy is negative, okay, negative 0.5. And how about the next one? Negative 0.5. Okay, so this would be a negative 1. And then we'll come over here. What kind of a slope is this guy? So 1, and then what kind of slope is this? 0.5. So I ask you, in part B, in the first graph, are the slopes getting bigger or smaller? The numbers, as the number is getting smaller. Negative 0.5 to negative 1, that's smaller. That's a decrease. What's happening with part D? Are the numbers getting bigger or smaller? They're also getting smaller. So yeah, I mean, Nikki is kind of feeling like there's a difference here, but somehow they're both concave down. Somehow the second derivative is negative for both. It's because you got to think about the signs too. It's not enough to just say steeper or shallower.
Also, if the trend in D kept up, eventually just look like
That's right. Yeah, D eventually looks like it wants to turn into B. That's good, right? I mean, like it's becoming that. It's transitioning quite nicely into that. There's a change in terms of whether it's going up or down, but there's no change in terms of are the slopes getting bigger or smaller. Good. Okay, number 11. What kind of a graph has f double prime equal to 0? We've seen f double prime tells you concave up or concave down. And by the way, I feel like it's pretty easy to remember that thing that's at the top of the screen. If f double prime is positive, and you know that the answer is either concave up or down, okay, positive is associated with the word up. That feels pretty good to me. Concave down, negative is associated with down. So like they kind of work the way I expect them to work. But what kind of a graph is neither concave up nor concave down? So it could be a horizontal line. Yeah, it could be any line actually. Because if I just draw any old line, and then I think about drawing a tangent line at this point, and at this point, and at this point. So I'll draw these tangent lines in green, and I'll draw them really small. But do you guys agree that the tangent lines are all just the line itself? So what's happening to the slopes of those green lines as you go to the right? They're all the same. They're all exactly the same. So it's not concave up because the slopes aren't getting bigger, but it's also not concave down because the slopes aren't getting smaller. So any line has the second derivative equal to 0. Okay. And I really do like this idea of the building blocks because, like I said, you can make just about any graph that we draw with some combination of these four things. And so, for example, something crazy like the tangent function. Let's look at this piece right here. I don't have it in front of me, but is that A, B, C, or D? Something that looks like that. That's a D. And then how about the next part of it? That's what is it? I heard A and I heard B. A? Okay, so the tangent function is comprised of some D, and then throw in some A, and then it just keeps copying. And you can imagine like the craziest graph that you could find, like that rational function that we spent all that time drawing. You could really just decide, oh, okay, first it's some A, and then we get a little bit of C, and then it turns into a B, and we get some more A with a D after that. And, like really just think about like any kind of graph I'm asking you to analyze. Basically, you've got the signs of f prime and f double prime right there. Like this is just about everything we need in terms of analyzing a graph, because every graph that we draw looks like combinations of those four things. We cannot build a straight line with those. It's true. Burn. Yeah. All right. So 12 says label the graphs with their concavity. So what would you say about this first piece? Okay, so that's concave down, and the second piece is concave up. Now let's start writing it in the math way. Because the first piece is concave down, I can tell you that that f double prime is what kind of a number? Is it a positive or a negative for concave down? It's a negative. So then what we'll say is that for all the x's that are less than 0, that's all these x's to the left f double prime is also less than 0. We buy it? And can you write down a sentence for the other piece of this same graph? Doesn't have to be a big sentence, but it needs to say, here are the x's, and here's the second derivative numbers. So for all the x's to the right, concave up means second derivative is positive. Okay, let's try coming over here. So we haven't talked too much about trig stuff, but let's look at this. Let's look at this branch right here. Not part A, but part B. Okay, first of all, what can you say about the concavity of the green part here? That's concave down, and then the other part over here, that's concave up. So we're going to have sentences that look kind of like that. But here you don't get to just say, you know, like for all x is less than 0, it's this, because it changes many times, right? Infinitely many times. So let's just see if we can remember what the important numbers are for the tangent function. Tangent function has this vertical asymptote. Anybody happen to remember? All right, 1 vote for pi over 2. Any? Okay, seconded. Okay, so let's say that this guy right here is pi over 2. And how about this place right here where it hits the axis? That's pi. And then the next intercept, is it a 2 pi? Yes, actually, yeah, it goes by pi over 2. 1 pi over 2, 2 pi over 2, 3 pi over 2. Okay, can you write down some sentences like we did there, but for the tangent function? Okay, how are we doing with our sentences? So in this case, you need to really write out an interval. So for all the x's between pi over 2 and pi, that was this piece. The function was concave down. So the second derivative is what? Concave down, second derivative is negative, less than 0. Concave down. Oh, it's a lot of stuff to keep track of. And then for all the x's between pi and 3 pi over 2, that's this piece. Concave up means second derivative positive. Good?
You also want to put like something about like a equals all integer values.
Yeah, so we could really actually write out, because there's just a bunch of copies of the same thing, we could come up with a more general way to describe, oh, if you're between these kinds of intervals, then f double prime is positive. So yeah, like, you know, k times pi over 2 up to k times pi. Yeah. Okay, so I think that's good. So here's, you know, kind of one of the basic premises of today's class is that the second derivative has everything to do with concavity. If I ask you a question about concavity, you need to immediately translate that to second derivative. If I ask you a question about a second derivative, you translate that to concavity. Now, there's also a hand-in-hand thing with the first derivative and something else. What does the first derivative have to do with in terms of the picture? Increasing or decreasing, right? So we're starting to, like, it's just connections that we need to have. First derivative problems have to do with increasing, decreasing. Second derivative problems have to do with concave up or down. Okay, let's go to number, we can go to this thus part. If the concavity changes at a point, then one of two things is happening. So first of all, what can you tell me about the point x equals 0 for this first graph? It's undefined. So the second derivative at that point doesn't even exist, right? And that's one way that we can have a change in concavity, is you just jump over something where the rules change. If the second derivative doesn't exist, maybe that's a place where the concavity changes from concave down to concave up or vice versa. Okay, at this point, well, the second derivative exists at that point. Can you tell me what you think the value of the second derivative is there? It's 0. Because if I were to zoom in, like really, really zoom in, yeah. If I just showed you that and you didn't know it came from part of a tangent graph, what does that really look like? That looks like a straight line. And isn't that exactly what we said for second derivative being 0? The question is, can we get rid of that? Like right up above, we said, oops, right up above, we said if the second derivative is 0, then you must be coming from a line. So that means that this part right in here that looks really, really close to being a line, well, the second derivative must be 0 there. So that's another place where we might change concavity. To the left of that point, this point right here, it's concave down. To the right, it's concave up. How do you go from negative numbers to positive numbers? Well, you hit 0 in between, right? So that's another important thing for today. If I ask you to figure out where the concavity changes, we want the second derivative to be 0 or undefined. Those are the candidates. Mm-hmm. Yeah, so what's true here? Is this a first derivative? Is the first derivative important at that point, or is it the second derivative? It's the first derivative. At that point right there, what's the value of the first derivative? It's 0. But the concavity just zips right past that. Concavity doesn't even notice that there's something important happening there. So here's something that that I did not see when I was a student in calculus class. I made up a little sketchpad thing. I never had a sense of like what the actual number of values were for the second derivative. I could say concave up means second derivative positive, like I had that, but I never really had a numerical sense. Like you guys can estimate first derivative by drawing what? A tangent line, and then you estimate the slope. So we have practice estimating like numerical values of the first derivative, but I never really saw when I was a student estimates of the numerical values of the second derivative. All I could say was positive and negative, but I never really saw numbers. So here's some numbers. So the point that we're focusing on is above this red dot, which I'm going to move around, and it's right there. And there's the tangent line. And if I move this guy, you can see the tangent line just kind of follows around, right? Okay, so nothing special. We've seen stuff like this before. So let's talk about that point right there. First, is the function increasing or decreasing at that point? Increasing. Does increasing have to do with first or second derivative? It is first. And if the function's increasing, then the first derivative is what kind of a number? It's positive. And so you can see, all right, so right now x is about -1.5, and indeed, the first derivative is positive. The slope of that line is about 1.8. Super. But now let's think about the concavity. At that point, are we concave up or down? We are concave down. So is this a first derivative or second derivative question? Second. And if you are concave down, the second derivative is what kind of a number? Is negative. And indeed, at that point, second derivative is, oh, okay, it's -9. What does that mean to say? I mean, like it's not the slope. It's somehow the rate at which the slope is changing. So here's what I'm going to do. I made these little buttons here. If I click on the button, the point jumps to x equals -3. You can see it there. And then if I click, then it just jumps over to, I just wanted to make jumps of like single units, just so we could kind of be consistent with where we are. Okay, so I'm going to ask you to remember a number. At that point right there, the second derivative is -18. Okay, I don't know what exactly that means, but just remember that number. Sorry, forget that number. Remember this number. The slope at this point is 22. Fair enough. That's the slope of the tangent line. Remember the number 22. Then I'm going to move 1 unit to the right. And what is the slope now? Slope is 7. It went from 22 to 7. Did it get bigger or smaller? It got smaller. 22 to 7. Smaller by how much? 22 to 7 was actually 15. So it got smaller by 15, yes? So in some sense, the second derivative had better be something around -15 so that the first derivative changes by decreasing 15. So let's take a look at the second derivative back here. I'm telling you, it should be something around -15. Here, it's -18. It's actually the derivative, the slope of that line is changing at -18 units per step to the right. If this function did if it stayed exactly as it was, it doesn't, it starts to curve. But if it stayed exactly like that, I can tell you right now that the slope would decrease by 18 if I just stepped 1 to the right. Every step to the right, the slope of that tangent line would get 18 smaller. But it doesn't, it starts a little bit curvy. And so when we go over to here, the slope is actually only -12. The tangent lines are getting, they're getting smaller, but not by as much over there. They were getting smaller much faster at the bottom. Those slopes are getting smaller a lot faster at the bottom than they are here. Remember, we had said the difference was negative 15, right? And what can you say about the two second derivatives? Here it's negative 18, and then here it's negative 12. And okay, it doesn't always work out that negative 15 is like right in the middle, but it's a cubic, and I think it always actually works out for cubics. Yeah. Okay, so here's what I'm going to do. I'm going to hide that.
So because it worked out perfectly like that, that means the fourth derivative is constant.
Yes, which actually makes sense. Again, we don't have that power rule, but the power rule says the power comes down by 1 every derivative you take. Yeah. Okay, so at the moment the first derivative is, actually I'm going to jump over to some place you don't have information about. So how about right here? At the moment the first derivative is negative 2. Remember that number. And then I'm going to jump one space to the right, and the derivative is positive 7. Negative 2 to positive 7. By how much did the derivative change? Positive 9. So positive 9 should be roughly the value of what? Of the second derivative. That's what it should be. Should be something around positive 9. So let's go back to there, and then I will unhide. There it is. So we were here. We said the second derivative should be something around positive 9. Here it's 6. If I jump to the next point, it's 12. Positive 9 happens to be perfectly in the middle. It doesn't need to be, but yes, those numbers, 9 makes sense. So it's hard to see without like actually having numerical slopes, but if I gave you slopes of tangent lines, you could estimate the derivative. Sorry, the second derivative. Second derivative tells you how the slopes of the tangent lines are changing. Is that helpful? Is that worth anything? I have not done this in a class before. Worthless. Thank you, Chris. Okay, so that is that. Oh, okay. One more spot I wanted to talk about. Let's drag this guy over to, say, up here. Okay, so if I get it right, then the slope of the tangent line there is about 0. And then if I go to the right, what kind of slopes will I get? I'll get negatives until we get to where? Until we get to that other 0, right? So all of these slopes are negative in here, yes? And that's confirmed by looking at the first derivative numbers there. Negative, 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 negative. But somewhere in the middle, and I don't mean in the direct middle, but someplace in there, there's a spot where the derivative is most negative. Yes? The derivative is the most negative because it goes from 0, and then it's negative, 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 but then it's got to get to 0 again. So someplace in there, it's most negative. And so now what I want to do is I'm just watching that number, trying to get that as negative as I can. And it looks like negative 5 is the most negative I can make it. Okay, so at that spot, the derivative is as small as it will be, which means that for just a little bit of time in there, the derivative isn't really changing much. Can you imagine something that goes like negative 1, negative 2, negative 3, negative 4, negative 5 at the bottom, and then it works its way back up, negative 4, negative 3, negative 2. So at the bottom, kind of imagine this like almost parabola thing. What kind of tangent line do we have down there? It's a 0. So how is the first derivative changing? By how much is it changing when we're right there at the smallest? Not by very much at all, right? It's really at that bottom part where it's not changing. And so how is that confirmed? By the numbers that you see up here. The second derivative, it's just about 0.
So if you had a problem where it was like asking which velocity was the greatest, you could get the second derivative of that, solve it for 0, and that would tell you the velocity was the greatest.
Yes, and we will do problems just like that later this semester.
It's useful.
And also, what can you say about the graph to the left of this black dot? Okay, it's increasing and then it's decreasing, so that's not consistent. But what is consistent for the whole graph to the left? It's yeah, it's true. X is negative for all the stuff to the left. It's concave down the whole time. Yes, to the left of that dot is concave down. To the right of that dot, concave up. Concave down means second derivative is what kind of number? Negative. So negative second derivative, and then over to the right, positive second derivative. Well, what number is right there in the middle of the negative second derivatives and positive second derivatives is 0. And that's a place where the concavity changes. And we had said, oh, if you want the concavity to change, probably want to figure out where the second derivative is 0. And that's where it's 0. Okay, so I realized that things get quite murky when we go, like first derivative is I think we have a good handle on it. Like this is going to take some time because there's a lot of questions that we can ask, a lot of words that we need to think about. Positive, negative, increasing, decreasing, concave up, concave down. It's a lot of stuff. So be patient with yourselves as you just try to digest those ideas. So let's just do this last part real quick, and then there's a good group activity that follows. We'll go to 13, and I think we're at Tiffany. Third derivative. Right, we could talk about taking another derivative, third derivative. And here's a bunch of notation. F triple prime, b cubed, dx cubed. Looks exactly the same as the second derivative notation. B cubed y over dx cubed, y triple prime. Toby actually knew this part before, so we'll get Toby to read the next sentence. Yeah, so this is one of the more lighthearted names that we give, but okay, so it's not really meant to be lighthearted. It's meant to be like if you have a sudden change in acceleration, it's a jerk, right?
Like
I mean,
you're robbing somebody else's dreams.
So if you're driving and you just jam on the accelerator, you might have a jerk, or maybe better if you're on a roller coaster and it just jerks you because there is a sudden change, not necessarily in velocity, but a sudden change in acceleration. If you're rear-ended, that would by some jerk, then you would experience a jerk, right? Okay, and then finally, we kind of stop writing all these primes at the third derivative because at some point it becomes really hard to see, like to count them. So if you're after the third derivative, we generally would put the number of the derivative up there in the parentheses. So that f parentheses 4, it doesn't mean f to the fourth power. Without the parentheses, that's probably what it would mean. But with the parentheses, it means, okay, it's the fourth derivative, but I don't want to hurt your eyes by putting 4 little tiny slashes and asking you to count them. Okay? Yeah, absolutely. I mean, you could do F2 to mean what? Second derivative. Yeah, it's not so common, but you could. We could do Roman numerals. All right, so we have 15 minutes, 14 minutes. Your job is to see how far you can get. There are 4 questions here. Your job is to write down the intervals where the derivative is positive or negative, the intervals where the second derivative is positive or negative. Again, focus on writing those intervals. It's only the x's that we care about. Only the x's when you write those intervals. And then on the next page, there are a couple of questions where you're going to draw some graphs based on original graphs.